No matter how powerful a centrifugal pump is, it cannot lift water from a depth greater than 10.3 meters. Beyond this theoretical limit, it stops working. To understand why, we must first correct a common misconception. Pumps do not pull water. In fact, no pump can truly pull water. In nature, water moves because of differences in energy. Water flowing down a mountain begins with high potential energy. As it falls and strikes rocks and trees, it transfers some of this energy and gradually loses it. A centrifugal pump works on a similar principle. At its inlet, known as the eye, the rotating impeller creates a low-pressure region. Atmospheric pressure outside the pump is therefore higher and pushes the water from the high-pressure region towards the low-pressure inlet. At sea level, atmospheric pressure can theoretically support a water column of about 10.3 meters. Beyond this height, it cannot push the water any further. Since the pump itself does not pull water, it cannot lift water beyond this limit. In practice, however, centrifugal pumps usually reach only about 7 to 8 meters. This is because they cannot create a perfect vacuum, and additional energy is lost through friction. This limitation is where the submersible pump becomes useful. A submersible pump is not fundamentally different from a centrifugal pump. Internally, it operates on the same basic principle. The main difference is that it remains fully submerged. So instead of drawing water from below, it only needs to push it upwards. This design is highly effective and is also used in oil wells, where such pumps can operate at depths of around 1 to 2 kilometers. Both centrifugal and submersible pumps use an impeller fitted with curved blades. Imagine sitting at a point near the center of the impeller. As the impeller rotates, centrifugal force moves you toward its outer edge, leaving a low-pressure region behind. Water then enters this space to replace what has moved outwards. However, the impeller cannot pump air, so it must already contain water before operation begins. This preparation process is known as priming. If the impeller or suction pipe contains air instead of water, a centrifugal pump cannot lift water. The pump suction line must first be filled with water, usually through the outlet or a dedicated priming opening. Only then can pumping begin. Centrifugal pumps also face a serious problem known as cavitation. As the pump creates low pressure at the inlet, the boiling point of water decreases. If the pressure falls too far, the water can begin to form vapor bubbles. At high altitudes, such as in the Himalayas, water may boil at around 70 degrees Celsius rather than 100 degrees because the atmospheric pressure is low. A similar effect can occur inside the pump. If the pressure at the impeller inlet falls too low, vapor bubbles begin to form in the water. These bubbles are then carried into a higher pressure region where they collapse violently. Over time, this repeated collapse damages the impeller surface. This process is known as cavitation. The passage between two impeller blades gradually becomes wider towards the outer edge. At the same time, the blade speed increases with radius, raising the angular momentum and total energy of the water. The expanding passage also reduces the water's relative velocity, converting part of this energy into static pressure. After leaving the impeller, the water enters the outer casing known as the volute. Its purpose is to collect the water and guide it towards the outlet. As the volute's cross-sectional area gradually increases, the water slows down and more of its velocity is converted into pressure. This allows a centrifugal pump to deliver water to a considerable height through its outlet, even though its practical suction depth is limited to around 7 to 8 meters. A submersible pump uses multiple impellers arranged in stages. Each impeller operates on the same principle, but the water leaving one stage must be directed smoothly into the next so that its pressure can be increased further. For this reason, a stationary component called a diffuser is installed after each impeller. The diffuser collects the water leaving the impeller, reduces unwanted swirling, and guides the flow toward the inlet of the next stage. As the water passes through each impeller and diffuser stage, its pressure increases progressively. Before leaving the pump, the water passes through a check valve, which prevents reverse flow. If the pump is switched off while delivering water to a great height, the water column above it begins to move downwards. Without the check valve, this returning flow could rotate the pump in reverse and potentially damage the motor. Everything discussed so far belongs to the pump section. To rotate the impellers, the pump requires a motor. Submersible pumps commonly use an induction motor which may operate on either a single-phase or three-phase supply. Inside the motor is a strong and durable squirrel cage rotor. The rotor contains conductive bars connected at both ends by end rings. These bars are slightly skewed. although the purpose of this design will be covered in another video. With very few components that can fail, the squirrel cage rotor is exceptionally robust. This reliability is one reason the induction motor is often called the king of industrial motors. Instead of ball bearings, this motor uses bushes, which are plain bearings that keep the rotor centered. Over time, these bushes wear down, allowing the rotor to vibrate or even make contact with the stator. Worn bushes must therefore be replaced. The rotor is relatively heavy and the impellers also produce a downward axle force while pumping water. This combined load is supported by a thrust bearing at the bottom of the motor. Inside the bearing, a thrust disc rotates with the rotor, while the graphite pads beneath it remain stationary. A thin film of liquid between the disc and the pads provides lubrication. It may seem that the rotating disc should rub directly against the stationary pads and generate considerable heat. During normal operation, however, the two surfaces remain separated by the lubricating liquid. The liquid between the pads and the thrust disc forms several thin layers. The layer closest to the rotating disc moves at almost the same speed, while each successive layer moves more slowly. Near the stationary pads, the liquid remains almost still. This layered motion allows the disc to rotate without directly rubbing against the pads. Stator windings surround the rotor. When electrical power is supplied to these windings, they produce a rotating magnetic field, which causes the rotor to turn. The motor generates heat during operation, so effective cooling is essential. In a conventional centrifugal pump, the motor remains above the water and can be cooled relatively easily. A fan mounted at the rear circulates air around the motor casing and removes heat. A submersible motor, however, operates underwater and requires a different cooling arrangement. Two common methods are used. The two common methods are oil cooling and water cooling. In either design, the motor is filled with oil or water around the rotor and stator windings, then completely sealed. During operation, this liquid absorbs heat from the windings and transfers it to the outer casing. The casing then releases the heat into the borewell water surrounding the motor. Cavitation also occurs in a submersible pump if the inlet pressure becomes too low. However, the risk is generally lower than in a surface-mounted centrifugal pump because the pump remains fully submerged. If you found this breakdown helpful, consider liking the video and subscribing for more engineering deep dives. We've got some exciting videos on this channel that we want you to check out. Thank you for watching. Keep engineering.